Good morning,
Good
sir.
morning, sir.
Good morning, sir.
Okay, so previously we were discussing about the hardness testing to evaluate the hardness, that is localized deformation, resistance of localized deformations of a material, and there means previously we have discussed about the different types of hardness, like we can uh, we can do the scratch test, we can do the indentation hardness test, we can do the this indentation hardness test statically or dynamically. That means we can put a dynamic load, okay, that is depends on time, or we can just keep a load that is fixed, okay, and based on that how we can predict that materials are deforming, okay, or how we can see that the materials is deforming depending on the type of load or the loading pattern. Okay. Now, means among all those three different types of hardness testing process, we are only focusing about the indentation hardness, where we basically apply the compressive load, and based on that we evaluate such certain numbers, and then we try to differentiate the different material hardness. So, considering only the indentation hardness test, we have seen that this hardness testing can be carried out different way, like by using different type of machines, um, and each machines have the different specifications. Like if I talk about the raw coil hardness testing, then then this particular testing process said that first you have to prepare, or you prepare the specimen, and the specimen should have the two parallel surface. First you have to means metallographically polish the surface quite well, um, and then you can use it, you can put it on the anvil of the testing machines, and then you have to apply certain minor load, let's say for 10 kilo, to stabilize the specimen. That means after applying minor load, what will happen, your sample will be fixed at a particular position, no lateral movement will happen, and then based on the hardness of the machines, you can apply certain amount of measured load. Now I said that you can use three different type of loads you can apply, and based on those major loads, we can differentiate the rock oil testing process, like rock oil A, rock oil B, and rock oil C. And in rock oil A, we said that we can use the indenter, that is barrel indenter, that is made of diamond. And we know that the diamond hardness is very, very high. So we can take the hardness of any material from softer to harder material. Okay. But the problem is, in each and every rock oil hardness test process, basically we are getting some numbers, but for the representing that which material is hard and which material is soft. But the problem is, when we take a large number of samples having the variations of hardness which is very large, so in that particular cases it will be very difficult to differentiate the the hardness of those samples. Just like if you recall the more hardness scales, where basically we try to make a scratch on softer material using the harder materials. So that is why we just set means according to mode, we suggested that we can differentiate the hardness based on the 10 different numbers, more hardness number, which we can call it. And like more hardness number 1 to more hardness number 10, something like that. Okay. But the problem is, there is means there are not only the 10 materials we have, more than means a lot more materials we have. So if a material, for an example, if I talk about the steel, then according to more hardness scales, the steel hardness varies within the number of 3 to 8. Okay, even 3 to in general it is 3 to 6, but in certain cases we can find more than that. Let's say I have a low carbon steel, then maybe the more, according to more hardness number, it will vary from 3 to 4. So more specifically, if I talk about the one is IF steel, which is low carbon steel, and another is high strength low carbon steel. So in these two sample, it will be very difficult to um, differentiate the hardness or the resistance to deform locally by following the more hardness number. So therefore, in this particular cases, we can obsolete, or we can find certain restrictions to identifying the hardness of a material. So therefore, the several other process has developed time to time. Okay, so one of such examples like Rockwell. So if we differentiate the hardness of mild steel and the high strength low carbon steel, which have the chemical compositions are nearby. Okay, if we if we carefully measure the hardness, then we can find there is a vast difference in hardness. So if we follow the Rockwell method, then also it will be quite easy to differentiate the hardness, because we see that in Rockwell scale, if we follow the Rockwell A testing process, then we will find the two different numbers. And as I said that during Rockwell hardness testing, when we apply the major load, then let's say we are applying the major load of 60 kilo, then depending on the 60 kilo, some amount of depth of impressions will form at the metal surface. And which materials means a soft material, obviously, the indentation depth will be much more in softer materials as compared to the harder materials. So if we carefully measure the depth of indentations, then based on that we can get a Rockwell hardness number. And in general, we find when the depth of impressions is high, then we can get the lower hardness, Rockwell hardness number. Okay, and when the depth of impression is low, that means we are getting the higher, Rockwell hardness number. Now, by seeing the hardness number, we can differentiate the two different material hardness. Okay, but we cannot always use the Rockwell layer. That is because we cannot, though we are using diamond indenter, and if we use this hardness, if we follow this hardness testing process, we can get a variation in hardness number. But certain cases we will find that they are, when we compare these things, then sometimes the numbers will merge, or sometimes these values are are such a confusing that it will be very difficult to differentiate the hardness of two different material. Let's say I am talking about the lead materials, and similarly I am talking about uh, uh, means carbide steel, means tool steel. If I talk about, then if we follow the Rockwell A testing process, then we will find that lead will give the lower hardness number. Okay, but the problem will happen when we have a very thin material, lead material, or thin lead material, uh, and then the depth of impressions would be so high that the impressions will start from one surface and it may end at the other surface. And when this kind of things will happen, then the anvil over which we are putting the samples, that will interfere your hardness data. So all these things keeping in mind, we try to we try to separate the we try to categorize the samples, okay, and then we try to measure the hardness. Like uh, uh, first we try to categorize the hardness based on the hardness of a material, means primarily, okay, like soft material are put together, and then we keep the name, let's say for soft materials. Intermediate hardened material, we keep it like the medium hardened material, and for high hardened material we can categorize in such a way, okay, that the high hardened material, we will measure the hardness by following the Rockwell C testing process, where we use the diamond indenter. Okay, for soft materials, we can use the Rockwell B. We can follow the Rockwell B testing process, where we can use the hardened steel wall. Okay, and then we have seen that for Rockwell B scale, there has certain load range, like it varies from the maximum load range that was decided, that is 100 kilo. For Rockwell C, the maximum load that was for 150 kilo. Okay, so why this kind of differentiations is there? That is because if we use very hard material for Rockwell B, then the problem will arise on the indenter, because in Rockwell B scales we are using the steel ball indenter. Now, if you know the steel hardness, okay, the hardness of steel, but if you are using cemented carbide, and if you want to measure the cemented carbide on Rockwell B scale, then what will happen? Your material hardness is very high as compared to the indenter. Now, if you put the samples on the end wheel, and if you try to indent using the steel ball indenter, then your steel ball indenter will deform. Therefore, it creates some problems, like when your steel ball will deform and it will flatten, then no impressions will be there on your interest material. Okay, therefore whatever readings the machines will show, that is completely wrong. Okay. Similarly, if we think the opposite, like you are using very hard material, but you are using very low load. Okay, and though you are using the Rockwell C machines, but if you use very low amount of load, then maybe that load is insufficient to deform significantly. So therefore, we generally categorize as materials based on their hardness, and after categorizing the samples or materials, we use the different category, or we follow the different category, different Rockwell testing process. Now, in the Rockwell testing process, it is not necessary to prepare the sample surface which is very smooth. Okay, it is not necessary, because here we see only the dial. Okay, and by seeing the dial, we try to measure the hardness number. Okay, but in certain cases, we specifically need to measure the depth of indentations, or depth of the depth of impressions, or the surface area of the indentation, projected area of the indentation. Okay, and all these things is required to more specifically characterize, or more specifically measure the hardness. Okay, though here whatever numbers we are getting, that is relative value. Let's say I am talking about Rockwell B scale hardness and Rockwell C scale hardness. So when we try to measure the hardness of Rockwell B scale, we cannot compare that particular hardness number with Rockwell C hardness number. Okay, so that is the thing. Like for very soft material like aluminium, we have got a hardness number, let's say RB 40. Okay, and for Rockwell C scale, when we measure the hardness of hardened steel, okay, then maybe we may get the hardness number of RC 30. So then, can we say that RC 30 is means the hardness of hardened steel is less as compared to the hardness of copper? That is no, because in RB scale, whatever numbers we are getting, we can compare the hardness only when we take the hardness only by following the RB scale. Okay, like RB 40, RB 50, RB 60, and based on that we can just say that RB 60, the material which gives the RB 60, so that material is hard as compared to the material which gives or which show the hardness number, that is RB 40. Now, when we choose or there must have certain technical justifications that a material to measure the hardness of a material, which testing process we need to follow. So first, what we need to do? First, we need to go for Rockwell C testing process, and there we need to find out the hardness number, that is RC number, that should be lies from RC20 to RC70. Okay, that is the valid hardness number range. Okay, because in RC scale we are using the maximum load of 150 kilo. So and that is a fixed load. So at that particular load, if the material hardness shows the value within this particular range, then we can continue our test in RC scale. But when the value, whatever the value we will get, that values is beyond this particular range, then we may choose the other testing process, or we may find the other testing process like RB scale. Okay, so that means the value should be less than RC20. So then only we can shift to take the hardness on RB scale. But certain cases we may found that particular values may goes beyond to the RC70. But that is the major issues, like when your sample thickness is very sample thickness is very low, your the machines is interacting to contribute the hardness, which that is why you are getting the hardness number more than 70. So in that particular cases, it is misleading to choose a particular hardness testing process. Rather, we need to fix the sample size, or we need to fix the testing machines. So
Beyond 70, we use the RS scale.
Yeah, RC. I'm talking about RC.
No, beyond 70?
Beyond 70 means in that particular cases, that is the maximum hardness number for RC scale. So in that particular cases, you have to think of that whether your sample is correct or not, like sample thickness is correct or not, or your machine is malfunctioning. Okay. So you have to check.
Okay, sir.
But yeah, if it is less than RC20, then of course the material is too soft. So then in that particular cases, we have to choose the RB scale. Okay. Okay. Now in our laboratory, we can find the Rockwell testing machine just looking like this. Okay. So here you can find the dial is there. Okay, and this is the anvil, okay, over which we can put the sample. So one of our fellow has prepared the samples just like this, and before placing the samples over the anvil, he makes sure that the two surfaces are parallel with each other, no inclination is there. Because if inclination is there, so what will happen, one surface are resisting to deform the material intensively, but another surface which is at lower position, so lately that particular portions will impose the resistance. Okay, so therefore there has certain heterogeneity to contributing the resistance. Okay, so therefore we try to make the two surfaces which is parallel with each other. Okay, and during testing, what we try to focus, that we always try to take the hardness nearby to the center regions, because if we take at the very edge, then maybe the samples will tilt or samples will bend, samples will tilt basically. And once the sample will tilt, your proper alignment will be disturbed. Okay, so therefore we try to restrict our to take the indentation nearby to the middle region. Okay, and and whenever we take the indentation, so first we place the samples, then we have to apply the minor load, and means when we apply the minor load, your indenter will just touch over the sample surface. Okay, and then we have to check that any lateral movement is happening or not. And when we apply the minor load, if we follow the dial very carefully, then the dial indicator will shift from one place to another place to show you that yes, you are correctly applied the minor load. Okay, and when we apply the minor load, basically what happens, your some amount of elastic deformations will happen, no plastic deformations will happen. Okay, uh, but here we try to fix that minor load, that is 10 kilo for harder material. Okay, if we use a very soft material, then of course we have to change the minor load from 10 kilo to, let's say, for 3 kilo or 5 kilo, something like that. Let's say for we are taking the hardness of lead, then we cannot use the minor load of 10 kilo, then we have to reduce it from 10 kilo to 3 kilo, 2 kilo or 5 kilo. Okay, whatever standard said, so we have to follow that particular standard. Now, after applying that minor load, for a particular machine, so we can see that the maximum load, the major load has set. Okay, and then just we have to pull the lever such that we can apply the major load, and then after applying the major load, your indicator will rotate. Okay, that means the depth of indentations is gradually increasing. Okay, and then one certain times you will find that your indicator become fixed, and then when you find that your indicator get fixed, applying the major load, then you have to give minimum 15 to 30 seconds, such that the permanent deformations will be stabilized. Okay, that particular time is called the indentation time or the de-welling time. Okay, so fixing that time, what you have to do, you have to release the load. Okay, major load. You have to release the major load. When you release the major load, what will happen? Your elastic deformed parts will recover. So when you find that your elastic deformed part is recovering, so then again your indicator will shift from one place to another place. Okay, when you apply the major load, means maximum depth of indentations you can see by seeing the dial. Okay, and when you are releasing the major load, then depth of indentations is changing from higher value to a little bit lower value. Okay, so therefore accordingly your indicator will shift from the lower number to a higher number. Okay, so therefore when ultimately you will find that your indicator become fixed, then you have to measure the dial. Okay, you have to see the dial and you have to measure the hardness number. Okay, so this is the correct procedure to measure the hardness following the Rockwell Rockwell B or Rockwell C testing process. If you have any confusion, please let me know. Okay, so here this is the standard. You please follow this standard where it has clearly mentioned that how we can take the hardness, or as I said, there are three major hardness scales are available, like Rockwell A, B, and C. But basically, we use Rockwell B and C because Rockwell A covers the whole range. But sometimes it will create some problems when we compare the hardness of very soft material to very hard material. So therefore, we categorize the soft material for Rockwell B scale and hard material for Rockwell C scale. Okay. Also, we can do the we can measure the hardness like surface hardness of a material or coating hardness of a material. So in that particular cases, we can manipulate the major load as well as the minor load, and based on that, we can differentiate the scale like Rockwell N, Rockwell L, Rockwell F, which are rarely used. Okay, so you need to focus only Rockwell B and Rockwell C for our cases. because this particular testing process mostly used in the industry, because industry they try to evaluate the material hardness, or try to find out the material homogeneity, whether it has achieved or not. So to see that, they try to do the process which is very rapid. Okay, so therefore they try to follow the Rockwell hardness testing process. But in research purpose, or in very stringent cases where you need to evaluate the hardness very accurately, so then this testing process is the use of testing process is restricted. Okay, therefore in that particular cases you need to go for other testing process like Brinell hardness test or Vickers hardness test. Okay. Yeah. Now the limitations, we are talking about the limitations. So the precautions during Rockwell testing process. What you need to do, you have to take the minimum 5 hardness number you have to collect. Okay. Why 5? You will find that whenever you take one hardness in indentation, you want to put one indentation, you will find certain numbers. Same samples, if you put the indentation in nearby regions, you may find the another number. So then you will get confused that which number is correct. Okay. So therefore, we have to take minimum 5, indentations. We have to put a minimum 5 indentations. Maybe you may get 5 different numbers. Maybe you will get, 3 different numbers or 2 different numbers. So therefore, we have to take the average values, and you have to be very sure that the variations of the hardness number should not exceed to a certain values. Okay, if it exceeds, then you will assume, or you will think of that your material, there is a problem in material homogeneity. Maybe some prior indentations or prior deformation has happened on the metal surface, that is why the number is varying. So then we have to take more than 5 numbers. Okay, more than 5 hardness numbers, maybe 10, maybe 15, something like that, to categorize the, or to characterize the hardness of that material. Okay, and whenever you put the 2 different indentations on the metal surface, you have to keep in mind the gap between 2 indentations should be more than 10 to 8 to 10 times, of the indented diameter. Now, why this is so? That is because one indentation, if you put on the sample surface, then of course some plastic deformations will happen. And when the plastic deformations will happen, some strain hardening will be there. Okay, that means it will intensify the load bearing capacity. And that is why if you put the next indentation nearby that particular prior indentation regions, so that means the load bearing capacity will increase as compared to the prior indentation. So what you will find in the next indentation, you will find the hardness number that is more than the previous one. So therefore, in order to avoid that, you have to take the next indentation, which is 10 to 5 times diameters of the indenter. Okay, the gap between 2 indentations. These are a few advantages. So I will share this slide. You please go through those slides, means where limitations and advantages has been described, considering the different points. Okay, so please go through that. Now I'm talking about the next hardness testing process that has developed by the Jonathan Brinell, and he suggested that we can measure the hardness by using a hardened steel ball. Okay, and the load can vary. According to him, the load can vary from 3,000 kilo to 500 kilo. He has categorized the 2 different material, that is hard material and soft material. For hard material, he suggested that we need to use the 3,000 kilo load, and for that particular load, if we need to use the indenter, hardened steel ball indenter, that size is 10 mm. Okay, and for soft material, the size of the indenter is 10 mm, but the load we have to manipulate of 500 kilo. That is because if we use 300 kilo for soft material, then the depth of impression will be very high, as well as the diameter of the indentation should be high. Okay, and he suggested that if we want to get the correct BHN number, that is Brinell hardness number, then the ratio of indentations and the indenter should be in a particular range, and that he specified the range that is from 0.25 to 0.5. Okay, um, because if we go less than that particular value, then the value of the hardness value, that would be overestimated value. That means the hardness of that particular material would be very high if we find that the indentation diameter, small d, which is very, very less as compared to the capital D, that is indenter diameter. Then that means that particular load is insufficient to put some indentations on the material. That means we have to increase the load. Okay, and when we increase the load, the problem may arise on the indenter. Okay, because we are using the hardened steel ball. So that means when we find that small d is very, very less at very high load, maybe indenter get deformed. Okay, or that means we have to use the different indenter that is made of very hard material, maybe diamond. But in Brinell test, we find that there is no such kind of indenters are available according to Brinell. So then we have to obsolete that particular test. That means we have to avoid to take the hardness of that particular material. Okay, so this is the restriction for Brinell test. Okay, now in laboratory scale, it is very difficult to maintain the load of 3,000 kilo or even 500 kilo. So in order to manipulate the load, Brinell has suggested that if I will show you the machine. So if you see, sorry. Yeah, if you see the equations according to Brinell, he suggested that we can measure the hardness number following this sort of equations, where we need to put the load value, we need to put the indenter diameter, and we need to put the indentation diameter. Okay, this sort of equation he has developed only by measuring the depth of indentation, that is T. Here you find the T. So he has measured following the geometrical relationship. So will you be able to measure the T? If I give the indentation diameter capital D, so will you be able to simplify the T, the depth of
We can
indentation?
convert it like
Yeah.
Yes, sir. Yes, sir.
T minus.
Yeah. That is capital D minus
Root over d square minus 1d square.
Yes. So if you just simplify this thing, then you can easily. This is the actually basic equations. Okay, base equation. Now here he replaced the T in terms of capital D and small d. So therefore, finally, you will get this particular equations. Okay. Now, by measuring those things like small d, by knowing the capital D and P, you can able to calculate the hardness number, that is called the BH hardness number. Okay. Now, here following these equations, you can also you can also simplify these equations in this particular format, where you need to know about the phi values. Okay, phi means the angle, this particular angle, phi values, and how this phi is related. That is, the small d by 2 is equals to capital D by 2 sine phi. So here, if you see this particular graph of the schematics, you will find that this particular diameter, or half of the diameter, that is capital D by 2, that is equals to small d by 2 by sine phi. Okay, so if we follow this particular relationship, and if you replace the small d with capital D, then the final equations would be just like this. Okay, but here the thing is, this particular things it applicable when your phi values is constant. Okay, that means by following these relations, you can make a proportional sort of equations, like P is proportionally related with the D square. You can put this particular relationship only when your phi is fixed. Okay, And following this particular relations, you can change the load as well as you can by changing the diameter of the indenter. Okay, like standard process, I said that 10 steel ball you can use, and following 10 steel ball, you can you set the corresponding load, either it is 3000 kilo or 500 kilo. Now, if you want to reduce the load, let's say for 300 kilo or 100 kilo or 120 kilo or even 250 kilo. So accordingly, by following these relations, you can change the diameter of the steel ball. Okay, so following this relation. But here the trick is you have to fix the phi value. That means you have to know that your phi value is fixed in these two different cases. Like one cases you have checked the D is 10 correspondingly the load is 3000, whatever indentation is happening. So in that particular cases, is phi value is a certain value. Okay, now after changing the load to 200 kilo, your correspondingly phi value should be in such a way that the phi value should be fixed. Okay, so this is the things you need to keep it in mind. Only if these things is maintained, then only you can change the indenter diameter. If it is not followed, then you cannot follow these things. Okay, and as I said that according to Brinell, the accurate hardness numbers you will get whenever you find that your small d by capital D varies from 0.25 to 0.5. Okay, if it goes beyond that particular value, like if this ratio is more than 0.5, that means you are using a too soft material, and you need to reduce the load. Okay, and you can decide the load in such a way that the range should be vary within this particular 0.25 to 0.5. So therefore you can find the limitations of this particular testing process. Like HP is dependent on the load for some sphere or some material. Okay, sphere means some the indenter, or similarly the HV is related, or HV is dependent on the load for the material that you want to find out the hardness. Okay, means it will be very confusing for certain materials where you are getting this particular ratio which is nearly 0.5 or which is nearly 0.25. Okay, so in order to overcome this sort of problems, the Vickers has suggested a testing process where
Sir,
he bolo.
can you repeat that last part about the ratio being between 0.25 and 0.5? And
Sorry. Please repeat your question.
sir, can you repeat that last part where you said that the ratio should be between 0.25 to 0.5 for Brindle
Yeah,
hardness?
yes.
Is this the
Let's
ratio
say,
small d by
yeah,
capital D?
yes, only by ensuring the small d by capital E. What you need to do here in Brinell testing process, what we need, okay, let me show you the testing machines. Okay, yeah. This is the testing machine, Brinell testing machines. Here we need to do is, we have to prepare the samples, making the parallel surface, to parallel surface, and place it over the anvil. And then you have to put the major load. No minor load is required here. Okay. And here in this particular cases, after applying the major load, the impressions will happen on the sample surface. And then what you have to do, you have to see you have to measure the indentation diameter, that is small d, by your own eyes. Okay, and after measuring the indentations through this viewing screen, then you will be able to find out, you will be able to measure the small d, and whenever you're doing this test, the indenter diameter. Okay, means your operators will tell you what was the indenter diameter and what was the maximum load. So here if you see, for this particular machine, your maximum load is 250 kilo. Okay, so if you follow the relationship, that is P by D square. Okay, so then you will be able to calculate the indenter diameter. Okay, so then by putting the indenter diameter, by putting the measured your small d values, okay, you will be able to find out that what was the small d by capital D ratio. Okay, and if it lies 0.25 to 0.5 range, then you can be so sure that your the measured hardness is correct, or the value whatever it will show or whatever you will find, that values is correct. But the thing is, when it goes beyond that particular value, then what will happen? Let's say the value small d by capital D ratio goes means it lies 0.5 to 0.6. That means in that particular cases, whatever load you have applied now, so that particular load is the that particular load is helping to deform the material more intensively. Okay, so then you have to reduce the load such that depth of impressions or will be less. Okay, so then you have to adjust the load. Okay, or you can categorize the metal which is from soft to hard. Okay, and for soft material I said that you can adjust the load from following the standard process. You can adjust the load that is 500 kilo in standard cases. Okay, and if you want to manipulate the load considering or changing the indenter diameter, so then you can set the load that is not 25 kgf, but you can set the load of 120 kgf or 100 kgf accordingly.
Sir,
Okay.
when the load is being changed, do we also need to check that the ratio of P by D square?
Yes, you have to check. Always you have to check. Okay, you can see that here the different load cells are attached, like 250, 187.5, 120, 100. Okay, and even below load cells are there. Okay, first, whenever you find that you don't know about the material hardness, so then first you can put any load cell. Okay, or you can put any load. Okay, then you have to measure the small d through the viewing screen. Okay, then you have to measure the ratio, that is small d by capital D ratio, and you have to check whether this ratio is lies within the specified range or not. If it is more, then you have to reduce the load. Okay, let's say initially you have put the load of 187.5 and you are getting the ratio that is more than 0.5, then you have to reduce the load. Okay, but whenever you find that your ratio is less than 0.25, then again you have to increase the load. Okay, so in this way you can manipulate the load.
So then when do we do the P by D square check?
Yeah, generally, when we manipulate the indenter diameter and manipulate the load, now initially what we think the two different categories. Okay, like for hard material, the maximum load is 300 kilo as per standard, and for soft material, it is 500 kilo. Okay, that is the two extreme point. Okay, and but it is not that for soft material it is the 500 kilo is fixed. Maybe we can reduce that particular load. Okay, but whenever we set the indenter, we just follow these two rules. Okay, that is 300 kilo or 500 kilo. Accordingly we can set the indenter diameter. Okay, and after setting the indenter diameter, you cannot change it. You cannot change the indenter diameter. Okay, but what we can do, we can change the load through this using this machine. Okay, so after once you have set your indenter diameter, so then you can change the load further. Okay, by following this load cell, different load cell. Is it clear?
Yes, sir.
প্রথমে কি বলতো, তোমাদের সফট মেটেরিয়ালটাকে একটু আইডেন্টিফাই করতে হবে যে কোনটা সফট মেটেরিয়াল, কোনটা হার্ড মেটেরিয়াল। এবার যদি তুমি হার্ড মেটেরিয়ালকে মোটামুটি একটা রাফলি আইডেন্টিফাই করে নাও, তখন আমরা কি করব, ওই 3000 কিলোর রেসপেক্টে আমরা তখন কি করব, ওই ইন্ডেন্টার ডায়ামিটারকে চেঞ্জ করব। লাইক মানে ওই রেশিওতে পি বাই ডি স্কোয়ার, ধরো একটা রেশিও আমরা পেলাম যেখানে পি এর ক্ষেত্রে 3000 কিলো পুট করলাম অ্যান্ড ডি এর ক্ষেত্রে 10 mm স্কোয়ার পুট করলাম। ঠিক আছে, সো সিমিলারলি P2 ভ্যালু, whatever the P2 ভ্যালু, সো P2 ভ্যালু আমরা এক্সট্রিম এটাকে নিতে পারি, বা হয়তো D2 টাকে আমরা ফিক্স করলাম লেটস সে ফর 2.5 mm, সো দেন whatever p value, p2 value we will get, so that value will be the maximum value. Okay, so we can change that particular maximum value in this particular machines. Okay, because here the thing problem is, once we can set means after setting the indenter diameters, we cannot change the indenter. Okay, rather we will change the load values. Okay, so by changing these things, we can just manipulate the things. So that is one sort of problem. You can also say that means it can create some sort of confusing, like one case is you are taking the two different material whose hardness whose hardness is nearby, and another case is you are taking the material whose hardness is means the difference between two hardness is very high. So in that particular cases, which loads we will consider, so that creates some problem. So that is why you will find the examples like for steel and cast material, you can find your BHN number is more than 100. But if you see the coppers and aluminum alloys, here you can say that according to BHNs, you will find the hardness value from 30 to 200 BHN. Okay, so then it will be very confusing for steel, for comparing the steel material hardness along with certain copper alloys. Okay, let's say one case is for steel materials you are getting the BHN 120 BHN. Okay, but in this particular cases you are applying the load of according to standard process 3000 kilo. Okay, but for copper alloys, as I know that as we know that copper material is soft material, so therefore as per standard we can set the load that is 500 kilo. Okay, but we are getting the hardness number, BHN hardness number, let's say 120, again 120. So then which material is hard qualitatively, which material is hard and which material is soft, to say it will be very difficult to say. Okay, so that is the restriction, or that is the limitations of this testing process. Okay, means which material is hard, which material is soft. To quantify that, we need to go for another testing process, and that is called the Vickers hardness testing process. And so in the limitation slides, you will find this sort of things. Okay, so the limitation slides here I have said the limitations of Brinell test. Though here few points I have mentioned, but you can also mention the points that I have said here or right now. Okay, but during test, whatever BHN numbers you will find at the extreme end. So here you will find that when your BHN numbers you are getting that is more than 65, then you cannot use this test. You cannot. You need to go for searching another testing process. Okay, here you are getting the BHN number 650. That means the material is too hard. Okay, maybe for measuring the hardness of that material, your indenter will deform. Okay, that is why indenter get deforms. That is why your hardness number you are getting that is very high, or the very little bit amount of indentation happens where the small d values is very very less. So that means in this particular cases you are overestimating the hardness of that particular material. Okay, so that is the problem for Brinell hardness test. Another things you can think of, like in Brinell test, we are trying to measuring the indentation diameter, that is small d, through the viewing screen. So when we measure the the diameter of the indentations, so the surface should be very smooth and very clear. Okay, such that we can correctly measure the small d values. Okay, if your surface is not smooth, if your surface is not properly clear, then there will be some error in measuring the small d. And the small d is very sensitive to change the BHN number. So therefore you need to prepare the sample surface following standard metallographic process. Okay, where the surface should be very smooth and clean. And just like the Rockwell scale, it is also very rapid test. and the value you will get that is little bit accurate. Though here I have said that accurate, but for material specific it is this accurate. I would say that it is material specific, because if you know the material very well, if you know the hardness range what it would be, so then if you follow the Brinell test and you compare the data, like copper alloys I'm talking about, if you only the hardness difference amongst the copper alloys or aluminum alloys or even aluminiums or as well as coppers, then you can easily take the hardness following Brinell test, okay, and compare the hardness amongst the material quite accurately. And the depth of and the gap between two indentations, it should be more than 8 to 10 times of the indenter diameter. So all these things you need to keep in mind. So these are the precautions you need to think of. Okay. Now in Brinell test, whatever hardness that we can measure, we measure the hardness by measuring the indentation surface area. Okay. Mayer, according to Mayer, he has also suggested that if we follow the Brinell test process, then maybe for some materials it gives some erroneous values. And some materials means, let's say one cases you are using an homogeneous material which is properly annealed. Do you know the different heat treatment process like annealing, water quenching? Do you know?
Yes, yes, sir.
Yes. Yes. So in annealing process, you know that first you need to heat the material at high temperature regions. Okay. Then you need to put the samples inside the furnace, and you need to switch off the furnace, and you have to wait for a longer period of time such that your room temperatures will attain. Okay. That means you are intentionally slowing the cooling rate of the heated material. Okay. So in this particular process, heat treatment process, we can assume that whatever microstructures will form at the room temperature, so that will be quite homogeneous. Okay. And the material will not contain any residual strain or stress. So therefore, if you use that particular material for measuring the hardness, you may get, or you will get a certain hardness values. But but prior to measuring the hardness, if you roll that particular sample and then again you are going for measuring the hardness following the Brinell test process, then you may get the Brinell hardness number which is relatively inaccurate according to Mayer. Why that is so? That is because in Brinell test, as we are using the hardened steel ball, and if you go for measuring the hardness for cold work material or deformed material, so the deformed material load bearing capacity has already increased. So therefore, if you again go for measuring the hardness, so then it will give some overestimated values, because the small d whatever you will get for that particular material, so that material is that things is relatively low. Okay. And why this is low? Because if we measure the indentation area, so the indentation area would be relatively less according to Mayer. So therefore, the Mayer has suggested that if we take the projected area, indentations area, so that will be more correct. Why? Because if your after cold working, your material hardness will increase. Okay. So then again, if you go for the indentation following Brinell test, so maybe your indenter will deform a little bit. Okay. Though sometimes little bit plastic deformation happen, but most cases the elastic deformation happen. But when the plastic deformation happens, then we can directly obsolete the testing process. But when elastic deformations will happen, we cannot avoid that particular error. Okay. So therefore, in that particular cases, the depth of impression should be relatively less. But if we take the projected area, then we can accurately measure the hardness of that particular material for cold work material. And according to him, he suggested that if we follow if we measure the hardness, then we need to take the projected area, that is pi r square or pi by 4 d square. Here d is the projected, projected area's diameter. Okay, diameter of the projected area. Okay, whereas in case of Brinell cases, we are trying to measure the depth of indentations along with the indentation surface area. But here only we are measuring the projected area. Okay, so pi by 4 d square is nothing but the projected area. Okay, so therefore, here whatever numbers we are getting, so that is based on the projected area. So when we compare the hardness of anneal material as well as for cold work material, so in these two cases, the mere hardness will give you the most accurate values as compared to the Brinell hardness test, because Brinell hardness test will give for cold work material, it will give the overestimated value. So we need to modify the testing process accordingly. Now, according to mere hardness test process, here, you can also find some relationship, empirical relationship with load as well as the indentations, diameter. Okay, so how it is related? Here you can find the relationship, that is P is equal to K D to the power n dash, and which is similar to the stress versus strain relationship during tensile testing that we have shown earlier. Okay, that is sigma is equal to K epsilon to the power n. Okay, so the important of deriving this relationship is because if we are able to measure the tensile test, okay, as well as if we are able to measure the hardness test, then we can correlate the variation in hardness with the variations of the tensile properties. Okay, let's say here for two examples I have given, like for fully annealed material, you will find that your load versus small d will varies in such a way that the small n dash will be 2.5. Okay, and this 2.5 is the summations of 2 plus 0.5. Okay, 2 plus 0.5, and 0.5 is nothing but the strain hardening coefficient, and the 2 is the value that can be suggested by the mirrors. Okay, so in that way you can relate the tensile property with the mere hardness values. Okay, so if you plot the hardness variations or the load variations with the indentation diameter, okay, like if you plot the load, the variations of load in the y-axis and the variations of the indentation diameter, the x-axis, then you will find that your load will vary, which is nearly equivalent to the load variation for the tensile test. Okay, so you please go through the book of details where this sort of graph has shown you that how the load generally varies for mere hardness test as well as for tensile test. Now, if you want to correlate the tensile properties with hardness, then according to Meyer or according to Brinell as well, it suggested that the hardness number will be 3 times of the yield strength of the material for spherical steel ball. Okay, so during tensile testing, whatever stress is required for like yielding of a material, you will find that for that material you need to put you will get the hardness number that is 3 times of the yield strength of the material. Okay, so in that way you can correlate that. Similarly, for true strain, if you want to measure or if you want to compare the strain that you are getting following the tensile testing, and you are measuring the indentation diameter, and if you want to plot that things, then you will find that the strain is related with small d as well as the capital D ratio in the following this particular formula. So all these things are empirical formula, means after doing the test, whatever data you are collecting, so you need to put the data in Excel sheet. Like in one columns you put the load, another columns you put the depth of indentation, another column if you put the indentation diameter. So if you have the large number data set, then you can plot the load versus the indentation diameter. Okay, then you will find some plot just like I'm drawing here. if this is load and if this is, small d. So maybe what you will find the load requirement, small d by capital D. So then you will find the load with small d by capital D ratios will vary something like that, something like this. Okay, and this may be for hardness test, maybe for tensile test. The things will be parallel with each other. Okay, uh, so that means the pattern should be same more or less. So this kind of plot you can draw by your own. And correlate the material property considering the hardness as well as the tensile property. Okay. Now, in order to overcome the Brinell problems and as well as the mere problems, mere limitations where they are using the hardened steel ball, and for very hard material, the hardened steel ball may deform. So, in order to avoid that, Vickers suggested that if we use the diamond indenter, and he also suggested a specific diamond indenter, which is this square-based diamond pyramid. Okay, and if we use that particular indenter, then we can get a hardness range that is HB. We can represent it as HB that can vary from 10 to 2000. Okay, HB. That means a huge range we can cover. Okay, for from very soft material to very hard material. And according to Vickers, he also suggested that we can also change the load. Okay, either it is from 1 gram force to for 120 kilogram force. Okay, and if we change the load, we can set that particular load based on the hardness of a material. But the thing is, the indenter shape would be fixed. Okay, here the thing is indenter shape would be fixed. So therefore, he suggested that if we follow the Vickers hardness testing process, then the number that whatever we are getting, that is totally load independent. Okay, just like in the Brinell case, what we are seeing, the number is totally load dependent. Means if we increase the load, accordingly the hardness number will change. Then it will be very difficult to quantify or quality means qualitatively it will be very difficult to measure the hardness. So in order to overcome that, Vickers says that if we change the load, so the hardness number will not change for same material. Like I have used like steel, and one cases I have set the load of 20 kgf, another cases I have set the load of like 40 kgf. So the two cases we will not get the two different hardness values. Rather, the hardness value should be more or less similar. Okay, so therefore he said that it is totally load independent. Now, how he set these values, or how he designed the indenter such that the load will be the value, the hardness number will be load independent. So to set that, or he take the advantage of small d by capital D ratio following Brinell hardness test. As I said that in case of Brinell hardness test, the load small d by capital D ratio should be 0.25 to 0.5. Okay, so in this particular range only you will get the accurate, more or less accurate hardness value. So this particular funda he has taken, means Vickers has taken, and he fixed this small d by capital D ratio, that is 0.375. 0.375. Okay, so using these particular relations, he measured the angle, okay, of phi. Okay, so here you can see that equations. These equations he has. First of all, he saw this particular schematic, and in this particular schematic, we have seen certain phi values is there. Okay, now if you take the tangent of, sorry, Just 1 minute. I'm drawing a tangent such that I can clearly show you the. So here you can see that if you follow this particular schematic, so can you see this particular schematic I have drawn? Hello.
Yes, sir. Yes, sir.
Okay. So here, if you follow this sort of schematic, then if you put the small d by capital D ratio, that is 0.375, which is fixed, and if you are able to if you are able to find out this theta values, the angle between these two red line. So if you find this angle value, so you will find that particular value would be 136 degree. Okay. So just do this sort of calculations by your home, means by yourself, and then you please try to find out the angle between the two straight line, red straight line. Then you will find that particular value will be 136 degrees. So that particular 136 degree he has kept fixed. Okay, and accordingly he made a square base diamond pyramid such that the angle between two surface is 136 degrees. So if you see this particular diamond indenter, square base diamond pyramid indenter very carefully, then you will find the angle between the two surface. Here you can find that there are four surfaces are available. Okay, so the angle between the two surface is 136 degree. Okay, so therefore if these things keep fixed, then that means we are fixing the small d by capital D ratio, that is 0.375. So therefore, if you change the load, so all cases you are fixing the small, the phi values, you are fixing the theta values, as well as you are fixing, accordingly, you are fixing the hardness number. Okay. And whatever means the impressions after Vickers test, the impressions that you will find, so the impressions will be like square. Okay, the top projected view, that would be square. So you have to measure the diagonal length of this particular things. No need to measure the surface area of this particular indentations. Just if you are able to measure the diagonal length, then you can directly measure the hardness number. Okay, so if you see the equations, yeah, if you see the equations, then you will be able to find out the hardness number. Okay, by following this equation, yeah, but the fundamental is the surface area of the indentations you need to measure by following this particular equations. But here as the angle between the two surfaces fixed, that is 136 degree, so therefore by putting the angle and as well as by measuring the diagonal lengths, you will be able to measure the hardness for a material. Okay, now this is the Vickers hardness testing process, and as we need to measure the diagonal angle. So that means the surface preparation should be very smooth and to accurately measure the diagonal length. Okay, and all the calculations for measuring the hardness, just like the previous one, the Brinell equations that he has developed. So here also, according to Vickers, he has also developed these equations to measure the hardness. And for simplifications, you can use these particular equations where HB is nothing but 1.854 into P by D square. Okay, where P is the applied load. Okay, so then, and D is the diagonal angle. So here, after seeing the impressions which have the two different diagonal lengths, so you can take the average value and you will be able to calculate the hardness number. Okay. Now, in the Vickers hardness number, by seeing the Vickers hardness number as well as by seeing the impressions, you can also think of that whether your surface is accurately polished or you're accurately, you have prepared the surface accurately or not. So you will be able to measure by just measuring the diagonal length. If you have any inclinations in the surface, you will find the diagonal length, that is D1, will differ from D2. Okay, so it will give a sign that you have to prepare the surface. You have to prepare the surface quite accurately, because if you have the two different diagonal lengths, so it will predict the error hardness value. So then accordingly you have to prepare the surface quite accurately. Okay. And another thing is that as you are using the diamond indenter, so the impression size would be relatively less. Okay, so therefore you can cover a you can take the large number of indentation data and then you can average it out to represent the material hardness of a material that is quite accurately. Now, after taking the impressions, you will find that three different type of impressions you will get. Like this is the first one, which is the most perfect type of indentations, where you are measuring the diagonal length, which is quite accurately. Okay, but this sort of impressions you may not get for material to material. Okay, like you may get this sort of impressions for annealed material or for very soft material. And why this sort of impressions you will get? Why not you are not getting the perfect impressions? Can you explain? Hello? Hello?
Deformation, plastic deformations.
Yeah, I mean, plastic deformation obviously happen, but why this pin cushion type of things can happen or will happen? Means your indenter surface is homogeneous, na? So
Yes, sir.
so if if we put the load, then gradually impressions will happen, and then during dewelling time the impressions would be the perfect. But when we unload the load, then again the surface, means this particular wall will approaches at the interior position. So why this kind of things will happen, or who is responsible for changing the shape? Which deformation is responsible for changing this shape? Is it plastic deformation or elastic deformation?
Elastic.
Elastic.
Means some sort of elastic recovery will happen. Okay, so that particular things can happen only for soft material or annealed materials. Okay, which is most predominantly that will happen, and this sort of things can overestimate the value. Okay, why overestimations is happening? Because at the corner, কর্নারে কি হচ্ছে, কর্নারে কিন্তু ইলাস্টিক রিকভারিটা ঠিকঠাক হচ্ছে না। কেন? Because corners are actually the stress concentrations at the corner is very very high. So at that particular corner, whatever load is applying, or whatever load we are applying, so that particular load is most significant to deform, most significantly. Okay, so that is why whatever plastic deformations will happen at the corner, that is much more significant. That is why whatever the recovery will happen, that is very very insignificant. But at the surface, what will happen? at the surface, the that the load is such a way that the plastic deformation is relatively less as compared to the corner. So that is why the elastic recovery will be much more significant. Okay, if we relatively compare these things, then we will find that elastic recovery is much more significant. So that is why this pincushion shape indentations you will find. Okay, so therefore after indentations, or when we measure the diagonal length, we will measure the overestimated value of D, and it will predict, the small hardness numbers, or it will give the smaller hardness values. Okay, but in case of for cold work material, or for deformed material, okay, or for very hardened steel, very hardened material, we may get the different scenario. Here, though the elastic recovery will be there, but some constraint effect, the ridging phenomena will affect to measure the diagonal length. Like, material will flow, at the surface. Okay, some bulging kind of things will happen at the surface. So therefore, you will find that your shape will be look like this, but your diagonal length is whatever diagonal length you will measure. So that is the value of this diagonal length is relatively less, as compared to the perfect indentation shape. Okay, so that particular things is actually underestimating the underestimating the hardness number, because actually it should be more than that particular value, whatever D value you will measure. So actually it should be the more than that particular D value. So that is why we always try to get this perfect indentation, but it is not on our hand. So that is why whenever we try to represent the hardness number, we try to see that what is the particular shape of the indentation, whether it is pincushion type or barrel type. If it is barrel type, then we say that whatever number or whatever hardness value you get, so the actual hardness would be more than that particular value. Okay, and the reverse things can happen in case of the pincushion shape indentations. Now, depending on the load that you are applying, you can categorize this weaker hardness indentation, which is micro indentations as well as the macro indentation. Okay, macro indentation means you are applying the major amount of load, and your impression size would be relatively high. So that means if you want to put the impressions on the material surface, it will cover the most of the area of that particular sample surface area. Okay, therefore whatever, let's say you measure the hardness 10 times, so that means it will may cover the whole surface area of 10 mm diameter square surface area, and whatever value we'll get, that will represent the overall material hardness. Okay, so in that particular cases, we try to get the macro indentation, macro hardness of a material, which reflects the overall material hardness value. But certain cases we may not want to find out the overall material hardness. Certain cases we may found a specific region of your specimen, like you have the coat of copper chromium coat. You did some coating on the material surface, and you want to measure the hardness of that coat. So in that particular cases, you need not to measure the material hardness, rather you need to measure the coating hardness. So in that particular cases, you need to reduce the load, you need to reduce the impression size such that it will restrict on the coating surface area as well as the coating thickness. Okay, that means the plastic deformation region should be restricted on the coating zone. So in that particular cases, we need to go for the micro indentations. Even we can go for the nano indentations, where we can manipulate the load from 1 kilo kgf to 10 kgf, or even 1 gram force to 1 kgf. Okay, so whenever we try to manipulate the load from 1 gram force to 1 kgf, so that is called the micro indentations. And when we manipulate the load from 1 kgf to 120 kgf, so that is called the macro indentation. Okay, though there has certain other reasons to to proceed towards the micro indentations, or even we can go the nano indentations where we can set the load less than 1 gram force. Okay, that is in the nanometric level. Okay, so so the reasons for choosing the micro indentations or the nano indentations. So I will discuss about these things considering only the microstructures of the specimen. Okay, so I'm just putting another. Yes, I think all of you have heard about the phase diagram of iron carbon diagram. Maybe you may heard about that. Like if we have a steel material, so how basically the steel material is developed in the industry, means how the microstructure of the steel material can develop. So in order to understand that, we need to study the phase diagram, and we can manipulate the phase fractions according to this phase diagram. Okay, for real examples, if I give, then I think you may see this particular rod that we generally see in the constructions area, like building constructions area, and basically this things has made of steel. So if we want to see the interior of this particular steel material, then we have to cut that material and we have to make the smooth surface. Then following standard metallographic techniques, we have to prepare surface. Then if we check the microstructures of the surface, then we will find that the different microstructural features that is available on the different zone. Okay, here we are using the simple rod, that is TMT rod, TMT rebar. So here you can find the three distinct different zone. Okay, at the centers you will find the different microstructures. At the surface you will find the different microstructures. At the intermediate zone you will find the different microstructures. Okay, so now if you want to go for the macro indentation, so what you will find at the surface area, you may find you have applied the same load, right? At the surface, you will find the different hardness value. At the center, you will find the different hardness value. But if you want to raster the hardness from center to surface, the variations you can clearly see that how it has varies. Now the thing is why this variation happens. If we want to know that, then we need to study about the microstructure, means how the microstructures are contributing to change the macro hardness of that particular material. Here you can see that at the center, the white portion, white microstructure is there, and the dark or the gray microstructure is there. So these are the two different microstructures. I think mechanical people and the production people, they may know about the pearlite and ferrite microstructures. Okay, and
Yes.
do you know, na?
Yes, sir. Yes.
Yes,
Oh,
sir.
okay. So if you know that, then you may also know about that the ferrite is relatively soft as compared to the pearlite. Okay, and if we have the martensite, just like in this particular cases, so martensite has even the higher hardness values. If you have the mixed kind of microstructures, maybe the hardness would be intermediate stages, like not it is very soft, not it is very hard, but at the intermediate stages. So if you have the microstructure which is fully comprised of this homogeneous microstructure, okay, that is mixed microstructures, you may found that the sample macro hardness is same each and everywhere. Okay, but if you found or if you find that your sample microstructure is different at different positions, then following the macro indentations, you will find that at the surface the hardness is high, at the interior the hardness is relatively low, at the intermediate stages the hardness is intermediate. Now that is because at the center it is composed of the soft phase as well as a little bit harder phases. So that is why the combinations of this hardness is giving the minimum macro hardness or minimum overall hardness values at the
So
center
what is
position.
DP?
DP is means a degenerated pearlite. Okay, that is the another variations of pearlite. In case of pearlite, we see this simple lamellae of ferrite and cementite. Okay, but in DP, the cementite part is fragmented. Whenever you find the cementite part which is fragmented, so in that particular cases we can call it as DP. So that is the material science part. So no need to go into details about that. Just
So is it harder than a pearlite?
yeah, it is relatively harder than pearlite.
Okay.
Okay, lamellar harder. Okay, so here the purpose of showing this particular thing is that how the phases is basically contributes to change the hardness. Okay, hardness of a material. Basically, when we find the hard macro hardness, which is same each and everywhere, so then we can think of that the sample microstructure is same throughout the cross sections of that particular of a specimen. Okay, so therefore we are getting the equal hardness each and every places. But the thing is, if you try to go for macro indentation testing, so then in this particular cases, the impression size, whatever you will find, so the impression size should be greater than the size of the microstructural units. Okay. Let's say here you can see the micron bar that is 20 micron. I don't know it is visible or not. So your impression size would be more than 20 micron, or even it is in millimeter range. So that means it can cover 5 to 10 microstructural units, or even more than that. In certain cases it is more than that. Let's say for 20 microstructural units, means I am talking about the grain size. Okay, so therefore, whatever micro hardness you are getting the average hardness of each and individual microstructural units. So that is why in macro indentation, that is giving the overall material hardness of a material. But for research purpose, if you want to find out that if you have the soft phases, just like this microstructure, you can find the ferrite as well as the pearlite. Black is pearlite and soft is ferrite. If you want to find out the hardness of soft phases as compared to the hardness of black phases, so then you need to reduce the indentation size such that it can covers only the area of the soft phase. Okay, it should not go beyond the area of the soft phase. Okay, then the black phase will interact with the changing the hardness of soft phase. Okay, so therefore you need to reduce the load, you need to reduce the impression size, then you need to shift from macro indentation to the micro indentation. Then you will find the hardness of the soft parts, soft phase, soft microstructures units, and then you will find the soft phase micro hardness is less as compared to the black phase. Okay, so for research purpose, we can go from the hardness testing from macro indentation to the micro indentation. Is that clear?
Yes, sir.
Okay, so from the microstructure perspective, it is okay. You can also think of like you can also think of like you have put some coat on the material surface and you want to check that, and physically or visually you are unable to detect that where the coating has happened accurately, where it has not precipitated accurately. So in order to check that, you need to go for the micro indentations or nano indentations. Okay, and then you can raster the indent. You can put the indentations on the whole material surface, creating a particular grid. Okay, means you put the indentations of the surface like 1,000 indentations you put following a particular distance or maintaining a particular distance amongst each indentations. Okay, and then you check that whether these things has happened or coating has happened each and everywhere properly or not. Okay, so this is another perspective where nano indentations or micro indentations generally carried out. And another things can carried out like if you want to check that how the deformation is carrying out, means like how the ferrite is deforming depending upon load. So that particular things can also be checked by nano indentation testing now, or micro indentation testing. Now, in this particular cases, what we try to find out, we try to find out the load versus displacement curve, load versus displacement data. So I will show you in the later slide. Yeah, in this particular slide, you can find that how the load is varying. Means here you can find that this is the initial positions of where we have not put the load. Now here, if you put the load gradually, you will find that your depth of impression is gradually increasing because the x-axis is depicting the depth of impressions. Okay, so therefore you will find that depth of impressions is gradually increasing depending on load, and once the maximum load is attained, so then you have to hold it for certain times, which is called the dewelling time. Then again you have to unload the specimen, and then you will find that due to elastic recovery, the depth of impression is quite recovered, and then you will find that how this deformation is gradually happening for a single phase material. Okay, and how this unloading is happening. Now, if you have a microstructure which is austenite, then you will find that during loading, what will happen? Load will gradually increase. Then once at a particular point, the load change will suddenly increase. Okay, means load will shift from lower position to higher position suddenly. So at this particular positions, what will happen? The phase is changing. Means austenite to martensite is changing. As you know that martensite hardness is hard, so that is why load bearing capacity will suddenly change. So in order to understand that, we try to go for the indentations of following the nano indentation technique. So you please try to understand that where nano indentation testing carried out, how it is carried out, or or after doing this indentation, what are the things we can also measure. Just like if we have this particular curve, by measuring the slope of this unloading curve, we can also be able to measure the stiffness of the material. Do you know the stiffness of the material? How stiff it is, how rigid it is. If you see the tensile curve, like the elastic Young modulus, so the Young modulus also decides that how stiff of the material is. Okay, the steel, for steel material, the Young modulus is nearly 200 to 210 GPO. So it is stiffer than the copper, whose Young modulus is less than 200, or means 100 to 150 GPA. Okay, or even less than that. So therefore, by measuring the slope in the tensile curve, we can measure the stiffness. Parallelly, if we do the hardness testing, nano indentation testing, by measuring the slope of this particular load versus displacement curve, and during unloading conditions, we can measure the stiffness of the material. So these are the things. Now, following the Vickers hardness test, by changing the load, we can change. We can take the we can measure the micro indentations or micro indentations or even nano indentation. There is and the phenomena is same, like the load versus surface area. Okay, indentation surface area. Whenever we measure the hardness following Brinell as well as the Vickers, we follow this sort of relation. Okay. Similar patterns can also find out when we try to measure the hardness following the new hardness testing. Okay, but here in new hardness testing, we can find that the indenter they are using, that is the different geometry. Here you can see that in case of Vickers testing, we are using square base diamond pyramid, where the base is square, but the height is the pyramid height. It contains the 4 different sides. Here also you can find the 4 different sides, but the diagonal length is different, because in this particular cases we try to create the penny shape indentations where the D1 and versus D2 is nearly 7:1. This particular ratio is maintained. Now, why noobs required to develop this sort of test? Because in case of Vickers testings, we are getting the square base, but it may take the surface area or indentation area which is relatively large as compared to the noob test. Okay, because in noob test we are just creating a penny shape indentations, and if we follow the noob test, then we can take n number of indentation, which is this n values is greater than the n number of indentations of Vickers test. Because because if you want to measure the hardness values quite accurately, we have to take n number of or large number of indentation, and then we try to average it out. So for a same material surface area, if we are able to measure the maximum number of indentations, or if we take the maximum number of indentation, then that is the most correct approach. Okay. Another purpose is that if we follow this particular shape, or if we want to put the impressions having this particular shape, then we can encounter the effect of prior deformation. Okay, because if we have this particular shape, then throughout this impressions, the plastic deformations we can intensively put on the material surface, because it is penny shape. Okay, and it is not homogeneous, the shape is not homogeneous. Okay, so that is why we can put the indentation, and that is mostly restricted over the plastic region. Okay, so that is the beneficial part. Okay, another thing is that um, we can also able to measure the hardness of coating material quite efficiently following the no hardness test. Okay, so but the thing is more or less similar, only the surface area that will cover by the no indentation test is or the indentation surface area is relatively less as compared to the Vickers hardness test. So if you compare this indentation size of a material, indentation size during indenting of a material, so you will find that if we have the Brinell testing machines, then for the same materials, you are getting the BHN number of 690, which can cover the indentation, the surface area this much. Okay, if you follow the Rockwell testing process, for the same material, you will find the Rockwell hardness HRC number 62, but it will cover the indentation area this much. If we follow the superficial Rockwell hardness test, then you can reduce the maximum load such that finally you will get the impression size that is this much. If you follow the Vickers hardness test, which have the Vickers hardness number like 750, but the impression size would be very, very less. So in all 4 cases or 5 cases or even 6 cases, you will find the different hardness number, but you are getting the different impression size. Okay. Okay, so now omitting all the limitations and omitting all the restrictions, if you just follow a single test method, then you have to think of about the sample size. Okay, think of about the sample size. For Brinell test, you have to have a large sample, large thickened sample, large surface area. The samples which should have large surface area. But if you go for the Vickers test, if you have only a very small sample, you can also be able to measure the hardness of that material. Okay, so that is the benefit of for choosing a sophisticated testing methods or choosing a sophisticated testing process. Okay, in noob testing also we can measure the hardness by taking the surface area, and for that here the thing is you need to take the unrecovered projected area. In Vickers test we are getting or we need to measure the indentation surface area, but here just like the mere case, here we need to take the projected surface area. Okay, so that is the difference between the hardness number, if we compare the hardness number of Brinell as well as if we compare the hardness number of noob. Okay, and of course you need to keep in mind that noob hardness testing mainly followed to measure the micro indentation or micro hardness of a material. Okay, so that is the things that is all about the hardness testing process. You please go through the advantage and disadvantage of the hardness testing process. Like if you use the Brinell and raw coil, most of the materials will deform. Okay, if you have very small sample, most of the material will deform. You cannot use it further. But if you reduce the impression size, okay, quite effectively, then you can think of to reuse the material further. Okay, so that is why you can say that the nano vicars or micro vicars or the micro noob indentation testing is one sort of non-destructive testing. Okay. Previous cases, whatever testing process I have said, like tensile testing and Professor, whatever he is saying, like fracture testing or grip testing or fatigue testing. So, and as well as I will teach you like impact testing and wear testing. So all these are the destructive testing. Means once we test the material, we have to throw away the material. We cannot reuse it. Okay, for service purpose. Okay, we have to throw it away. Okay, but if you follow the non-destructive testing such as micro vicars or micro noob indentation testing, then just by taking the hardness at the surface of the material, we can again reuse it. Okay, but the problem is in certain cases, like if you have the indenter which is very very sharp, you cannot take the hardness for very hard material or very brittle material, not hard, I would say brittle material, because that is the one limitations of vicar macro vicar hardness test, because you are using very sharp diamond indenter. So if you use the glass material or ceramic material to measure the hardness, then actually you are intentionally indenting the glass surface or ceramic material surface, and the glass and ceramic materials are very brittle. So once the impressions will be there on the surface, so once the indentations will happen, the material will suddenly break down. Okay, the material will suddenly fracture. So therefore we cannot go for measuring the hardness of glass and ceramic materials following the vicar hardness testing. If we want to measure it, then we have to manipulate the load as minimum as possible. Okay, if we want to measure it. But the thing is, there must have certain plasticity. Then only we can go for the vicar hardness testing. Okay, so these things you can categorize to only to talk about the disadvantage of vicar hardness testing. Okay, and of course, as we are measuring the hardness by measuring the diagonal length, so we have to prepare the surface very smooth. Okay, even for nano indentations and micro indentations, we have to be very sure about the microstructural surface, the surface of the material. That means we have to, polished in such a way that we can reveal the microstructure and to identify the microstructural components. And after identifying that things, we can take the hardness of individual phases quite accurately. Okay. So please go through this particular part. I will share with you this particular slide. So please go through it, and you can also take the reference from the book of data. Okay. And if you have any further queries, you please let me know. And from the next class onward, we will talk about the another testing process, that is destructive testing process, such as impact test or as well as the wear test. Okay, yeah, tensile test I have already covered, na? So in the next class we talk about the impact test. So if you have time, please take a small review about the impact test that is available on the book of return, and then I think it will be easier to you to understand that. Okay, I will share with you this particular slide. You can also take it as a reference.
Okay, sir. Thank you, sir.
ঠিক আছে. Okay, you may leave now.
Okay, sir.